All right, so we're live. So hey everyone. So today I want to be talking about manifold learning and how it relates to graph neural networks. And so I've already talked a lot about graph neural networks on stream. So if you're interested, I have a whole bunch of videos you can check out. But let's check out like how this specific problem is different. So typically, like what I've been talking about is like let's say you have like your input data could be like think of it like this is like an image, right? Or it could be like a sequence. So this is like image processing. Sorry, so yeah. So let's say then you feed this to some sort of like neural network. This whole thing, we typically call image processing. Most popular architectures are stuff like ResNet. Uh, in the case of a sequence, you feed it to a neural network, like this is NLP, and either this is RNNs or transformers now for the most part. Um, but I've been personally a lot more interested in graphs recently, and so with graphs, like you can think of it as it's like different nodes with edges representing the relationships, and you want to feed this to a neural network, and this is called a graph neural network. There's a whole bunch of algorithms, but I would say probably the most popular one right now is a graph convolutional network. Right, so this graph can be a whole bunch of stuff, right? So this could be social media, uh, it could be like a molecule. And these are all settings in which we're given the graph. So by given the graph, like that means like you're given the graph as some form of adjacency matrix. And then you have like some node level features, and then you have like some edge level features. This is how this typically, the problem is typically formulated. So what we're looking at right now is a bit different. So let's say, so let's assume the graph is implicit or latent, right? And so the difference here is like, let's take a scenario like point clouds. So you have a self-driving car, and it has like some lidar sensors at the front, and this is like sort of detecting like a human. So what's the lidar sensor gonna see? Like, well, it's gonna see some sort of like point cloud. Let's say that looks like this, for example. So this would be like, let's say, some sort of human in the scene, right? The reason it's points is because, like, by virtue of how LiDAR works. And so the problem we have here is how do we segment this into like an actual human? So in this case, well, the whole thing is a human, right? But then there's a couple of segments, right? There's the head, there's the body, there's the legs, and then there's the hands and arms, right? So this is, for example, if I took k equal to 1, 2, 3, 4, 5. But if you made this more granular, well, maybe you could separate up the left and right hand and stuff. So the reason this is a graph is because if you view it this way as a bunch of segments like this, then, well, you have a head, and the head is connected to torso. Torso is connected to a hand, and then these are the feet. So what looked like a point cloud actually has an implicit structure as a. Well, let me zoom out. I don't think it's showing. So what looked like a point cloud actually has a sort of like latent graph structure. So this is the head, this is the torso, these are the arms, and these are the legs. And so once we like basically the problem is twofold, right? Like we want to take a point cloud, right? So we want to take a point cloud. We want to turn this into a graph, and then we want to use GNN to do some sort of classification, regression, or generation. So basically, just do what we've already been doing so far. And so the reason why we call this like manifold learning in the first place is because it relates back to like an older research body in machine learning from like I would say like the 90s or 2000s, called manifold learning. And so the idea of manifold learning is this. So basically, when you typically work with data, you always work with like d dimensions, right? So let's say you can visualize up to three, for example, here. If you want to draw some sort of like 3D figure, for example, like let's say this arrow, and you can somehow like draw in 3D if you know what you're doing on something like this. Uh, but if it's more than four dimensions, it becomes very difficult to draw this. And the other thing is that typically machine learning algorithms take exponentially more time and are exponentially less good the more high dimensional your data is. So the question behind a lot of manifold learning is basically, is there like basically instead of having x and rd, is there also, let's say, an x prime in r k, where k is much smaller than d, so much lower dimensional, where the difference in, let's say, some sort of classifier f between f of x minus f of x prime is less than some epsilon, right? So what this means is that the difference, uh, so here, like, okay, so just reviewing because it was blocked again. But yeah, so initially we have like d-dimensional points. We want to see if this point, if we can replace it by a point in a k-dimensional space where k is much smaller than d, where the difference between the neural network outputs would be very small. And so basically, this is sort of like you can think of it as like the intrinsic dimension of the data. And I'll show you a couple of examples now. I realize this is fairly abstract if you haven't seen this terminology before. And this is sort of like the given dimension, and then this is your neural network. So the reason why like I say f, because like a neural network is basically just a continuous function. So it has like a weird shape, of course, like like the structure with layers and stuff. But at the end of the day, this whole thing is just equivalent to some function f. Right. So I actually want to go over a couple of papers. So just like zooming out here, I want to go over a couple of papers that discuss how to do this, and all of them have Michael Brownstein as one of the authors. So I would very, very strongly recommend, if you don't follow him on Medium, to do so, because his GNN blog posts are some of the most accessible and most precise, even though they're very easy to understand. So you can do that, and then I'm just gonna help you out in terms of guiding you, understanding like the details here, and then going like over the papers in a lot more detail and seeing like how they actually work. So the thing about graphs in general uh, is that if you're, let's say, trying to find, let's just take this as an example, right? So this is a point, right? Like and the idea is that you want to basically have like, but neural networks only understand like real numbers as vectors. So the idea is, how do you turn a node into a vector, right? So we want to go from node to vector. Well, the first thing to notice is that each node uh, has some features. So for example, let's say it could be uh, I don't know, like in the case of the point cloud, right? This would be your x, y, z coordinates. Like, so basically where you are, like where this point is in space. Um, and in this case, maybe in the case of this point cloud, it would be a set. But let's just assume that it's a single point to make this example easier. And so the idea is we want to have a feature for this where it takes in your current features. So basically, like featureized node is equal to node features plus neighbor features. And the way you do this aggregation is relatively straightforward. So it could be something like you take your current XYZ coordinates, and then you take the sum of the XYZ coordinates uh, for XYZ in neighbors, right? Something like that. All right, let's zoom back out so we can see everything. So yeah, so this is the main idea here. So you basically aggregate some node level features with some edge level features, and this thing just works. Um, so this idea is called This idea is called an edge convolution. So one of the paper we're going to be watching actually discusses this very idea. So we'll just check it out in more detail. But the main idea is like, well, why is this interesting? Well, because typically when we work with point clouds, people aren't used to this approach where you basically aggregate in neighboring information. So with algorithm, like the most famous like point cloud like network is called PointNet, and PointNet only looks at points and ignores neighbors, right? So it's sort of a simplifying assumption. But the framework we're gonna see right now like that doesn't do this. So the framework we're actually gonna take a more closer look at is called like dynamic graph CNN. And so they were first developed by Yue, I believe, Yue Wang and MIT. Uh, and so here you can sort of see how this sort of works, right? So the final result we want here is some sort of segmentation that looks like this. And in this segmentation, you can see like, well, the body is different, and then the engine is different, and then wings, and then and then there's the back. So these are sort of like the main segments behind this plane. And the way this works is that at every like we're basically gonna at every point have some sort of representation for each point in a segment, and you can think of this as being like a classification. So each point, so like this plane has, let's say, 100 points in it. Each 100 of those points, like, you need to classify to some to some class. So let's say in this case it's one, two, three, four classes. And so at every point, at every layer, you plot at which to which class does a point belong. And ideally, what you should see is that the end layers will have a very good understanding of what belongs where. But what's interesting, if you look at the earlier layers, you can sort of see what each layer focuses on. And so this idea here, for example, here, like let's say at layer one, you can see here that it's sort of focusing on learning how to classify the wings, and then here it's learning to classify like the rotors, like the engines. And eventually it gets to a point where you can just get the segmentation you're looking for. So as a follow-up work to this, this was a more recent paper, like the differentiable graph module paper. So this lets you sort of separate out parts of the problem here. So in this paper, the dynamic graph CNN paper, what they do is you're learning the graph and you're learning node features all at once. Whereas here, what they do is they sort of separate out the node feature learning from the graph feature learning. And that way it just becomes like more tractable, just because you're reducing the dimensionality of the problem. And so it becomes just easier to have things converge. But the core idea is the same. Um, but why do they call this like manifold learning, right? So I promised you that, like, well, like one example I gave you was here the idea that you could take something very high dimensional like this and then just turn it into this like very abstract graph, and it basically says the same thing. Like another example they give here, which is kind of interesting, is this one, right? So thank you for the subscription, Fox. I appreciate it. Like, you should come hang out on the 5th of November. Like, pleasure to have you on. Yeah, so anyway, so here, like, let's say we're looking at a data set that's trying to classify how your wrist is in space, right? So there's you'll see here that the like RGB pictures, right? So like an image. So let's say in this case is a black and white image. So like let's say it's an image that's of size 256 by 256, for example, right? So that means the dimensionality of this image is 256 times 256 times uh, 3 if it's a colored image, right? And this is this is what, like 256 times 256 times 3. Yeah, so this is what, over, like, this is about 200,000, right? Dimensional. Which is huge. Like, this is a very high dimensional space, but it doesn't actually like reflect what this data set is actually telling us. So in this data set, if you actually look at the images, there's two things that change: whether your wrist is rotated, and whether your wrist is rotated like this, and whether your finger is extended or not, right? So it's two dimensional. And so two-dimensional, okay, yeah, so you see here, like they actually say it's 64 by 64. Because this is black and white, like you just multiply this by one, versus comparing this to two, this is much lower dimensional, and it's actually much more indicative of what you're actually trying to do. So if you can do machine learning on a two-dimensional space, like it's a lot easier than doing machine learning on a, like 64 by 64 dimensional space. So the idea of manifold learning is kind of old, actually. So I was first aware of it in the context of, you may have heard of techniques like PCA, right? And so with PCA is you can imagine a data set, right? And then let's say you have some sort of tabular data set where this is like you have example one, example two, all the way to example n. And here you have feature one all the way to feature d, right? So, and then each one of these will have like some value here in the middle. So the idea here is that, well, this is an n by d dimensional data set. And so, same thing, can you make this n by k and not make the classification change all that much? And there is, in fact, like a way to do this called principal component analysis. So this is a matrix, right? And so you can basically look at how the matrix is oriented in space with PCA, and that can let you just get a much smaller matrix of size n by k. There's like a billion techniques to do this. You could just like pick three random ones instead of like doing it with PCA. You could learn it with some sort of machine learning model. Like there's all sorts of ways you could solve this problem. Yeah, so, but generally dealing with handcrafted features, like that's something people did quite a lot in the past. Like now, I think not as much. But another way to view this is, well, if your actual data set looks something like this, and so this becomes like, well, for each point, you have three values, right? So let's just draw this out. So you're gonna have your x, y, z coordinate, right? And then you have like 0 to n points. So this is extremely high dimensional, but if you could replace this into a graph that just has like like 5 by 5, for example, it's going to be a lot more tractable to do machine learning. So even though it doesn't immediately seem like it, learning a graph is basically a form of dimensionality reduction. And when you hear dimensionality reduction, this is similar to manifold learning. Like it's the same. It means the exact same thing. All right. So let's see. All right, so this is it. There's a couple of interesting papers mentioned, but you can use this for for like medical images. But it's mostly useful, I guess, like for point clouds because that's where it's like the most obvious where these things are needed. And point cloud is very useful for anything that involves like autonomy, so think self-driving cars, like robots, like anything that needs to see something in space. Like yeah, you could do it off of an image, but point clouds is just like much richer data, and so if you have that, like you should use it. Again, like an image, you can infer the 3D structure, but then that's like an additional problem you need to solve for yourself. So I already pulled out like the papers here. So before we go over the differentiable graph model one, I want to go over the dynamic graph CNNs for point clouds and just like talk through it a bit. So you'll see here that the actual structure of the network is relatively straightforward. Like you have like this point cloud, and then you make it go through like an edge convolutional layer. Then you have the first layer, and edge convolutional layer, and then you concatenate all of those features and have a multi-layer perceptron to do some segmentation output. So this is very common. Like this last step before you make a prediction, like it's very common to just have some sort of like basically flat layer. That where the dimensionality is equivalent to how many classes you're trying to predict. And in the middle, what we're basically doing is we have these edge convolutional layers that are going to aggregate local information for each point to figure out like which class it should belong to. And so let's talk about how that works. How that works right now. So here. So the idea here is that typically, like we have like this like whole complicated neural network over here, right? So where you're trying to compute features. Uh, And ultimately, from the point cloud that looks like this, the edge convolutional operation will update the feature of this node based on the features of its neighbors. And so there's multiple ways to do that, and they actually just talk about them here. So if you're interested, like this is actually the full structure of the network they talk about here. Uh, so here, for example, like when they talk about a spatial transform, six, like they basically have 6 dimensions because that's the dimension of what's called a transform. So each object in space typically has 6 things that determine where it is. So basically, it's x, y, and z. It's x, y, and z, and then so basically where it is in space, and then its rotations along those 3 axes. So that's where the 6 comes from. And so if you just look at this like more closely, like basically it starts off, you have this point cloud, it's 3, right? Because like remember we're working in 3D space. We then like bump this up to a higher dimensional space, and then eventually here go all the way up to 1024 dimensional space, and then finally make a classification output where it should be the same size of um, the of your output. So how does an edge convolution work exactly, right? So you can see here that they define an edge convolution by planning like a channel-wise symmetric aggregation operation like MT white square. So this seems confusing, but basically just think of this as an operation. It could be the sum, it could be max, it could be whatever you want. And in this case, it works over a function that's a function of both a point and its neighbors. So xy is the point and xj is all of its neighbors. So you can have a bunch of choices for h. So if h is just a summation operation, then you give each term, each neighbor its own weight theta, which you would learn. Or it could just be like you don't even look at the neighbors, you just look at the local features of the node, right? So here you don't even have an xj. And here you just recover point net, right? So this is just like this is just point net, right? And in this case, this is basically weights per neighbor that you would learn. So moving on, you could have like a couple of extensions to this framework. Well, you could have like, let's say some features that are local, and then you multiply that by another function that's a function of both the neighbors and its local nodes with some sort of Gaussian kernel. Uh, you could have it just be a function of the distance between the 2 points. So this is sort of like, like yeah, hey, yeah, manifold learning. So Christian is asking. I've always wanted to know how this works. I mean, yeah. So if you have any question, like feel free to let me know. But basically here, like we're coming up with a function that lets us figure out how to aggregate local features to compute node level features, right? So you could have a function that's like basically takes in two, both the node and the neighbors. You could have a function that just takes in the node. You could have a function that takes in the difference between them. So that's sort of a proxy for it. And this last option, I believe, is what they use in this paper is you take in a local node and then the difference between a local node and its neighbors. So this sort of like is a best of both worlds because it will like naturally give more importance to stuff that's closer to you. Uh, and then this sort of like looks somewhat complicated, but you just have like these weights for each of these terms, right? So it's like instead of having an arbitrary function, we're saying it's a function where we weigh each of these and then feed it to a nonlinear activation function. Uh, and that's pretty much it, right? So this is sort of like the main idea here. But moving on, you can sort of see here, like I actually like this a lot, where like in this framework that they propose, they show you how different networks sort of like reduce to each other. So like let's say in the case of PointNet plus, you have the function which is a function of just the yeah. So this paper is the dynamic graph CNN paper for point clouds. And so here, for example, you can see that this function here in this case is just a function of the current node when you're trying to do some sort of value. Here, it's only a function of your neighbors. Here, for example, it's a function of, let's say, yeah, so these look like both a combination of the function between you and your neighbors. And you can sort of see how this works, right? So here, let's see. Uh, So the structure of the feature space produced at different stages of our shape classification, visualized as the distance between the red point and the rest of the points. So here, for example, what we're doing is we're not learning anything. We're just taking the Euclidean distance between a point and another point to figure out where to classify it to. So in this case, for example, this is equally close to all of these. So it's going to classify all of these as the same, and because like here k is equal to 2, right? However, after making actually go through like a machine learning model, the features become a lot more meaningful. So for example, here, like it figures out that like, well, like that there's a guitar body and then there's the frets. Like it figures out that these are like different things. And by the way, these are typically labeled. So like the data set that people typically work with here is called the model net. So like none of this is auto magic. Like each point in the point cloud will have a classification, and you're doing supervised learning here. So ModelNet is, I think, one of the data sets that they use in this paper, but like another one here is like ShapeNet. I think this looks at the direction. But imagine if instead of just being a solid color, there were multiple colors here, and then the colors are indicated by some classes, and then when you're rendering this thing, you give it a different color if it's of a different class, and it just gives you a good idea of how these images are generated. Right? So when they're evaluating it, like they compare it to all sorts of stuff, right? But let's say I think the main comparison point would be PointNet. Like you'll notice here already, like PointNet is actually pretty good already. Like the accuracy here on PointNet is already like 86%, which is amazing, right? Like the fact that you can classify points pretty well just looking at local features alone. That said, in the case of point clouds, local features encode quite a bit. Like, sorry, like the node only feature encodes quite a bit because your XYZ coordinate is fairly indicative of where you are. But it's a fairly close, to, I guess, to using Euclidean distance as an aggregation function. And whereas here with their like with their approach, like they got closer to 90% accuracy, so we have like about a 4% bump in accuracy, which is a big deal, I guess, in this case, right? Especially at the tails, this makes a big difference. Another thing I thought was interesting was that like they also report like the model size here. So for example, their model is like probably as big as PointNet, but and it takes more time to classify. So they were actually still fairly honest that like, look, this can't be as fast as PointNet. But the other models here, that these why is this two different PointNets? Oh, there's two PointNets. Interesting. Yeah. Yeah. Never mind. So I guess like these results aren't particularly compelling. Like it's slower, I guess. They're just like being honest about it. So this goes back to here, like the segmentation, to sort of show you here what it would look like just anecdotally. So this is their approach. This is the ground truth. Like this is what the data set that they would be using. And here in PointNet, you can see that it looks, like there's some stuff that it just doesn't figure out how to do well. There's like these aberrations. Like for example, here for some reason it thought it was different. But what's cool is like here, like they just like render a whole bunch in this data set, and there's a couple of applications to this. Like let's say another one is indoor scene segmentation. So like you're taking like an apartment and you want to figure out where everything is, like what's the wall, what's the furniture, etc. Um, yeah, so this is the indoor scene segmentation. Yeah, so it's interesting. So these are like the real colors, and the colors in this case represent uh, actual classes. One way to think about this is like, well, you could also even generate this from a 2D image, using spectra stoganometry. I forget. Uh, strogar stroganometry. Photogrammetry. Oh yeah, sorry. Photogrammetry. But anyway, like so you could have like you could generate this with photogrammetry, and then do the scene segmentation, and then you can just get a pretty robust system to recognize stuff. So obviously, for anything with self-driving cars, robots is a big deal, but also like any sort of applications in augmented reality or VR even would be really interesting, right? Where it could figure out like, oh, there's furniture here, so let me make it so the environment actually has a wall there, as opposed to just having an empty space. So I think this is a very exciting space at the intersection of graphics and ML, but I will say, in general, most ML graphics work is fairly simple. So I do want to, if at some point, check out Keenan Cranes. So our lab used the lidar to get the point cloud ground truth. Does it even give you the classifications though? Like I thought lidar just gives you points. All right, so let's just quickly skim the next paper. So, in the case of the next paper here, they use like basically the main difference here is here. So what they do is instead of learning the node features and the graph at once, they sort of separate out. So you have a graph convolution where and then you have like I believe like probably like these edge convolutions here. So the difference between an edge convolution and a graph convolution is for a graph convolution, uh, basically think of it this way: like when you're using edge convolutions, you're basically aggregating info over nodes, and then GraphConv is aggregating over graphs, right? So basically, we learned the graphs. So just the points, then we have to do something like this for segmentation, I guess. Yeah, that's true. I mean, that's probably what use. And I think there's still like lots of hand coded stuff that people use in the community, especially if there's lots of domain knowledge, like let's say in cars or something. But if you want something to just work overall, I think the sort of like the data set approach is just like a lot more user friendly. So like I said here, like we have like, oh yeah, so actually it's the other way around, it seems. Sorry, we should flip these. But basically we learn the graph and then separately we learn the features on this graph. Otherwise everything looks like the exact same. Do they compare it to, yeah, so they compare it to their old approach here. And it does seem like it gets a lot better. I mean, yeah, so we're talking 84 versus like 91 here. And let's see. So I want node features, graph features. Right. I mean, again, I guess that's what's kind of cool about doing works in graphics. Like you can always have like these really pretty plots when you're working with stuff. Yeah, I also like this visualization here. Like they show neighborhoods, so sort of like here, like it gives you an idea of who's related to what. And I sort of like wonder, like with this new OpenAI work, if they did something similar, like sort of like rings of knowledge, or like maybe it's implicit in the data structure. So okay. So there's really one last thing I want to show you here. Because like most of this paper is actually discussing the experimental methodology. But I thought this part was interesting here. I thought this was, so okay. Basically think of this like a pipeline, right? So typically if you have a very large graph, then it's very difficult to do any sort of edge convolution on it because like let's say in the worst case your neighbors are the entire graph, then you sort of like want to split things up and tell because like why, right? Like let's take an example. Let's say there's a graph that looks somewhat like this, and you want to come up with some node level feature here. So you need to aggregate like features from your neighbors, but your neighbors also need to aggregate features from their neighbors, etc. So then this goes all the way back, and turns out like whenever basically to compute some node level feature, you have to do this like search throughout your entire graph. And to sort of set a cap on that, that's where the graph sampling idea comes in. And you're basically saying, for example, only do like k hops from current node, for example. So this idea is called graph sampling. Right? And so, but before you get a graph, before you sample it, what you actually need to do is generate the graph. And before you can generate the graph, you need to learn some features about all of the nodes in that graph. So this is sort of like how this work all fits in together. Yeah, so this is sort of interesting. So for example, even in terms of just generating the graph, like they make a fairly simple heuristic here, where they say like we look at the distance between two nodes, we square it, so now we're in L2 distance, and then we take the negative exponential. So this is still, I believe this is still a metric. So if these 2 points are close, then this will still be small. But this is sort of like what they call temperature optimized because it lets you control how sensitive you are to your neighbors. So if you increase T or decrease T, you can respectively decide if you want to have more or less neighbors be part of the graph. And this sort of depends on the kind of space that you're in. Like more nodes means more computational cost, uh, but potentially better accuracy. Less nodes but means faster, potentially more generalization. So Krishan is also asking, so if I was wanting to do procedural generation of shapes, are you aware of any work in the space that does similar things? Is this dynamic graph approach useful at all for this? Um, I would say definitely, right? Like because so if you can do a classification with this, then you can basically just adversarially come up with a generation, right? So I'd have to think about it a bit more, but I'm assuming that if you just uh, basically took where's the architecture? Actually, I think it's simpler to show in the previous paper. So if you wanted to generate stuff, what you would do, or like what I would do, is I would take the code for this code base, and I would basically copy paste this. Then I would invert the second part, and then you can generate it. So that's sort of like generic in general. Like anytime you have something that works well for segmentation, you have something that works well for. So then you end up with a sort of auto encoder architecture, in which case you can then use it to generate stuff. If you just basically only use the, the the second part, right? Yeah. So like auto encoder again, I think both should work fine. All right, so I think like let's just sort of wrap things up and discuss like what we discussed so far. So what we talked about today is basically typically in deep learning, we're working with images, in which case like ResNets are great. You're working with sequences like language, in which case like RNNs and NLP are great. Uh, but what I've been personally been really excited about has been graphs, and so the most popular algorithm I would say is probably graph convolutional network, where you just work over a graph. A graph has a very clear representation in deep learning as a matrix, where you have the adjacency matrix, you have the node features, and then you have the edge features, and then you feed them. You feed them in a network. However, in some domains like point clouds, the graph is implicit. Like what you're given is only x, y, z coordinates, but you don't know how all of those points relate as a sort of graph. What's interesting about setting things as a graph is that then you can just feed it to a GNN and then do some sort of classification, regression, or generation. And the graph is much lower dimensional than the original space. And so that way you can understand graph learning as a form of manifold learning. The main idea behind manifold learning is that it's sort of like an older line of research in machine learning, where you're trying to project points to a lower space, a lower dimensional space, so that models are faster, such that the differences in classification is negligible. So that's where this epsilon comes in. Specifically, when not now when we're trying to think about like how to actually learn these kinds of graphs, we basically can use basically learn how to aggregate local information from neighbors to get a node feature for the for your existing node, and use edge convolutions to come up with the with like a proper segmentation. The best way to think about it is I think the dynamic CNN paper makes it work really well. So you basically have at every point here basically classification class for every point in point cloud. And so you can see this very clearly if you go here. I think this is a great visualization. Manifold. I'm just using incognito because Medium really sucks with this stuff. Yeah. So basically, at every layer, all the nodes are basically going to give a prediction for which class a point belongs to, and at the very last layer, you would expect this to match the segmentation. At earlier layers, you see the network sort of focusing on different parts of a network, like the different segments. The main issue, so this is the dynamic graph CNN approach. The main issue with this approach, unfortunately, is that uh, it sort of like simultaneously learns graph level features and node level features at the same time. So what you can do is you can sort of like split these out as two different learnable networks where that still, of course, like share parameters with each other. And so this is the differentiable graph module. So it's a very similar idea in that it tries to reduce the dimension of a data set from a point cloud to a graph. Uh, just as a example, when you're trying to think of lower dimensions, you can think of stuff like PCA, but I really like this example about hands. So yeah, I mean, I hope this was informative. I think this is gonna be it for me for today. The next video I'm gonna do is gonna be a longer one. I'm gonna be doing, I think it's probably gonna be at least an hour, maybe even two, on deep learning on proteins and genomics. So it's a space I've been looking into for like the past year. And I think now with AlphaFold becoming so popular, it's sort of a body of work that I wanted to explain. Like, what are genes? Like, what does it mean to program them? Uh, Proteins let you just generate new materials, so you can just build shit biologically. We have DNA printers now, so I think this is like going to be a very exciting space where I think machine learning is going to really, really help. And where domain expertise, it's very difficult. I just think something like AlphaFold is definitely going to be in production in all pharmaceutical and genomics and protein companies. So I think just covering it from the ground up, like the theory of the bio theory of all this stuff, and then in addition the how biology can be framed as a machine learning problem. So yeah, I mean, if you enjoyed this, please subscribe, and I'll see you guys soon.